All right, well, let's go ahead and get started. Okay, I just gotta find my screen here. All right, so first, I'm gonna do a shameless plug for EcoFish. It's we're gonna be introducing this new fish mapping layer in the next 2 to 3 weeks, and it's gonna be the biggest. It's gonna be the biggest thing that we put out really since Biobase's inception in 2011. So just real quick, we'll go through just a quick slide on what EcoFish is. Just because it is so close, and I think you, many of you on the call will be interested in seeing what this is all about. So we're going to start mapping the fish echoes that's in your sonar file. Is there not going to be any additional data collection requirements? All of that data is in the SL2 and SL3 file. So here's an example of some fish echoes that you can see in the raw image. And our partnership with EchoView software, they are kind of the industry standard in processing hydroacoustic data for fish mapping, fish detection. So their algorithms pull out those objects. We're able to count. We're able to get a count of them, the depths, the relative size, acoustic size. Create these heat maps of the abundance, and then also have these automated reports that does counts and also the depth at which you find the fish. So that's going to be an add-on to any subscription. It's going to be $2,500 for unlimited uploads during the subscription period, or we have a one-off option, $4.99 for the subscription, and then the $800 add-on to that single one-off. But we're also going to have free trials and discounts for new users and academic and HOAs. So stay tuned on that. Okay, thank you. So first, before we get into kind of how do we design transects, how do we kind of execute a transect survey, talk a little bit about the basics of what a grid cell is, how does that affect Biobase outputs, what is a buffer, how does that affect Biobase outputs, kind of this jargon to kind of get our head around some of the basics of when you create an interpolated map. What are those components? Okay, so first, starting out with grid cell. Grid cell is also maybe more popularly known as pixels. You should get this. You should understand that. You know, especially with these cell phone cameras right now, I mean, the resolution is amazing and the detail is amazing. So you're really a lot of pixels, really small pixels, and a lot of them. The image on the right, very pixelated. And so think about this now when you're also creating a map. And I'm going to bring some of those concepts home. Think about this resolution is amazing and the detail is amazing, but you can't do that. You can't take a picture like that detail from outer space, or even an aerial image for that matter. Now, if you were to look at, calculate the data in each one of those pixels, like what is the color value in each one of those pixels? If you were to kind of look at an average color value, these would almost be identical. But obviously, they're very different in terms of the detail. So it's that accuracy versus precision argument. So, always kind of have that in the back of your mind. We now start to translate this to lakes and ponds. The default Biobase resolution grid cell, 5 meters. That might be too detailed in really large lakes. If you're surveying a 10,000 acre lake, it might be too detailed. If you want to do a whole lake study, but it might be too coarse in a small stormwater pond, and you can go down to a 1 meter grid cell, and so that might be the more preferred detailed. Okay, so we can go ahead. Let's park that concept for now, and we're going to come back to it very soon here. So the next concept to take a look at is this concept of buffer, and what Biobase does called blanking. And anything, and we have these defaults, so it's 5 meter grid cell, 25 meter buffer. We kind of use this 1/5 rule. It's a rule of thumb. You generally don't want to interpolate down to 1/5 of your transect spacing. So we have a 25-meter buffer, and that's on either side of the track. So if you have transects that are closer than 50 meters, you're going to have overlap there. If they're wider apart, you're going to see these gaps, and we blank out anything that's outside of that trip path. If you have small gaps in your map, you can increase the buffer. Before we get too far, I'm going to show you real quick where you can change those values. So you can do this on a trip-by-trip basis by going to the tools. We go to trip reprocessing, and then we can select the buffer that we want right there. And also the grid cell values. Here I'm applying that 1/5 rule. I've got 15-meter buffer, 3-meter grid cells. You can also do this in, I just want to draw your attention to the processing preferences. Every single upload will look to these preferences. And let's just say that you mostly do stormwater pond mapping. You're probably going to have pretty detailed surveys, pretty detailed transect spacing. I would, by default, set this to 1. And then every upload is going to have 1-meter grid cells. The buffer, you don't have to worry about the buffer. It's in this situation, I would maybe just change that grid cell to 1. You're going to have complete coverage of that storm pond. So I wouldn't be too worried about like extrapolating beyond, and shrinking down that buffer. But every situation is different. Okay. Go back to the slides here. Something to think or something to consider here. If I look at this map and I see these little gaps, I probably wouldn't have any problem just expanding that buffer to 40 meters is probably going to get this filled in. But keep in mind that it's also going to expand it this way as well. Interpolation generally is pretty robust. Extrapolation, you can have problems there with extrapolation. So just kind of keep that in mind. Okay, so we kind of talked about this. Yep, this is an example where I increased it to 50 meters. Now I got that all kind of filled in. All right. So let's go back to that grid cell question and the grid cell and buffer question. So in Biobase, you see this nice smooth map. You see these gaps. If we want to kind of drill down a little bit into what the data actually looks like, we're going to pull the data into GIS, and we export CSV. So this is right here, tools, export data, export CSV data. We're going to export I'm going to need to refresh my browser because this stuff's grayed out. So we're going to do that. So we're exporting grid endpoint as CSV, and then that's going to make it so so we can start bringing this data into GIS and do all kinds of fun stuff. Okay, so we're going to actually go to GIS to take a closer look at this. All right. QGIS, great open source, very powerful GIS platform. I know probably a lot of us, a lot on the call are Esri people, but QGIS for those of us who are not doing a lot of hot and heavy GIS stuff and don't want to pay the expensive license, it's a great alternative. So again, here is our, here you can see the data, how the data are collected. The data, let's just turn this off so it's not so busy. This is the data along the track, and those, the data are spaced, let's see, this one to this one is, okay, that's about 2 meters, anywhere from 1 to 2 meters, depending on your speed. And so this is the data of the single beam sonar along your track. And then when you export the data, export the grid data, then that exports the buffered data. And so now when you measure these distances, this was that when I said it was a 3 meter grid cell, when you measure these, it's give or take, but 2.5, 3 meters spacing between these. These are grid centroids, grid cell centroids. So we have some tutorials that can show you like how to then convert this into a raster. And it's pretty, it shows some interesting detail. So let's turn this one off, and let's just turn on the 3 meter one. That one is here, right here, 3 meters. Let's turn this. Yeah. Okay. So here you can see and this is just a depth map. So we converted these to a raster, and these are all of value. Along the track, the data are going to be very, very accurate. Some of these grid cells actually will have multiple data points in that grid cell. So that's a 3 meter grid. And let's just take a look at a 10 meter grid. Start to see that gets a little more coarse, a little more, pixelated, that concept. And then we can turn on the 30 meter. So you can see how different it looks between the 3 meter and the 30 meter. So where this gets to be relevant, right, is in a small pond like this, you're going to want to use that 3 meter or depending on your transect spacing. We'll get a little bit more into that. But here you can see, well, if I'm surveying and this is like a 75 acre lake. If I'm surveying a 10,000 acre lake, well, maybe I can expand these transects out and go more with this the 30 meter grid cell and, be okay at that scale of my question. If I'm looking at the whole lake scale, expand those transects out and use a bigger grid cell, and you can get that kind of lake level information. So if that's the scale of your question. All right. So that's kind of the concept of the grid cell buffer, and kind of sets the stage for the rest of the talk. This is a good case study, Lake Waccamaw. We're going to be spending some time in North Carolina today. This is a lake in North Carolina with a NC State partnership on that project. Hydrilla gets into the lake. They don't know exactly where it is. They need to do a whole lake survey, but they can't cover every inch. So, all right, we're gonna set up this 300 meter transects back and forth, and then they end up finding hydrilla, like surprise, surprise, by the launch. And so they did kind of this hybrid approach of, all right, we're going to do this course survey, but then we're going to do more intense survey at the launch.
Hey Ray, real quick.
So
Kevin
yes.
Johnson had a question. I don't know
Sure.
if you can unmute yourself, Kevin. And
I can wait till the end if you'd rather wait.
Well, now you might as well ask now.
Back to merging versus changing the buffer distance within, how you showed. So like for us, obviously, as you know, we're mapping a lot of bigger lakes.
Yep.
And we have pretty standardized procedures. We typically merge at 75% of our transect spacing just to make sure we fill in all of our gaps.
Mm-hmm.
But every once in a while, there'll be like still a blank area. Does it matter, or is it better to go back and remerge at a wider buffer distance, or is it okay to then just open that merge and increase the buffer distance within the merge?
You're going to be the best judge of what are the consequences of making an assumption. I would just expand the buffer. If you see if it's a kind of these little pock marks, relatively small, just expand the buffer and and don't worry about expanding the grid cell size too.
Okay.
I think
Yeah,
it's
that was
pretty
my other
pretty
question,
robust.
like how that,
Yeah.
whether remerging with a wider buffer distance or just going into the merge and increasing the buffer, how that affects the grid cell size and if it really matters.
Yeah. Yeah. I think the most efficient way to do it is just to go into the tools, trip reprocessing, and
Mm-hmm.
changing things there rather than deleting, remerging, and doing all that stuff. You can
Mm-hmm.
just go to the tools, trip reprocessing, and do everything you want there. And like I said, I would just increase the buffer in those cases. If you've got a standard operating procedure, but you have, like, let's say a transect goes off this way, or that, like, your sonar, it kind of winks out or something like that. I mean, you're, like I said, you're the best judge, but I would just increase that buffer.
And then those examples you showed with the different buffer distances on that one lake, obviously the reports for each of those merges, the the point data would still stay the same in the
Yes, that's
reports,
right.
but the grid values would change, right?
That's right.
Okay.
Yes, they will. That is a good point. Thank you. I can bring that up here. These automated reports, they do give you the metadata on what the settings are. And then, yes, what Kevin was talking about, will these values change? No, these values always stay the same. It's kind of more or less the raw data. It's these values that you'll see. The grid is what will change. Yep. So
Thanks, Ray.
great. Yeah. Yep. Good questions. All right. So this is just to say, we kind of already touched on this, but again, just be thinking about what are those the scale of my question. If you are doing property level work, you obviously, this is going to be a better, kind of better resolution survey on the left, and this is what you're going to want to do, but this is going to require, that 50-meter, transects versus something like this, the 300-meter transects. Not a lot of detail, but it's really interesting. The same overall kind of average value. So just something to think about. What's nice about Biobase is that it's really flexible. You can do these hybrid approaches. You can do different merges. You can do different designs. All right. More on the grid cell size. Again, 5 meter is the default. Here's an example of what that looks like. This is a concentric circle design. Again, really nice design in small ponds. It's just really easy to do with a kayak or you just follow your track around the outside and you kind of keep working your way in. An automated robotic boat works really well. You put in that mission planning in the mission planning software, and the thing just goes around in circles and comes back home. So it's real easy to do. Here's an example of the difference between the detail between the 5 meter default grid cell versus the 1 meter. Not huge. A nice smooth result here, but maybe you get a little more detail here. Maybe that's just a little more desirable. Let's get the maximum detail there in these storm ponds. All right, so we can now kind of get into different transect designs. Questions to consider. We already kind of talked about this. Scale of your question. It's a small scale you want to resolve change, and then really importantly, what's my budget? Time and money. We're not going to have unlimited resources, so where can we get by without sacrificing our objectives? Where we can maybe cut back a little bit. And I'll take you through some examples that might be instructive in that question. Okay, we already talked about that 1/5 rule. Yeah, speed of travel. Oh, are we painting walls or cabinets? That's just some kind of metaphorically. I think that's maybe the next slide here. Kind of an example. Are we going to be mapping a pretty kind of featureless bowl? If so, we can maybe the speed a little bit. It's kind of like throwing a, getting a roller. Your objective is getting coverage. I want to get coverage, and I'm just gonna really kind of just slap it on there. The detail, I'm not too concerned about that because it's all kind of a featureless moonscape, if you will, or whatever. But there are a lot of water bodies that people map that are very, very detailed, or that have got a lot of detailed contours and holes and humps and points and whatnot. And so in that case, you're going to have to take a little brush and get in those cracks and crevices and things like that. It's going to take more time, but it's just that's kind of the way it works. All right, so here's this example, this kind of this waffle pattern, this gridiron kind of pattern where you have this is really interesting when you look at these two images here and you just kind of superficially look at the detail. I can hardly see a difference between these two images, and this is 2 times the effort. So people around the office always know I like the saying, is the juice worth the squeeze? This is kind of textbook no, in my opinion. So I'd say, just stick with the 25, the 25 meter parallel transect in this example, and you're going to get you're going to get very similar outputs with less work. Okay, so if we layer on the concept of the grid cell here, you can see now you can start to see some sacrifices in detail. Here's this interesting mid-water feature, and as you increase, or if you as you decrease the transect spacing, you're getting less detail. Is that important to your study objectives? Again, it's interesting when you look at the average depth, it's only like 3.5% difference. So if your objective is to get kind of overall capacity, or to do some like water volume assessment of the kind of the different contours, that's pretty robust. You don't have to have really, really detailed transects to get a decent understanding of what's going on with water volume. But if your objectives are to get a good kind of baseline contour map, or if you're looking at doing treatments in an area or dredging, you're going to want an understanding of that detail. And then here's an example where this transect, if you get rid of this transect, that feature now just disappears from the map. If you don't have transects going over some feature, it's not going to be mapped. So concentric circle, like I mentioned, I won't go into much more detail there, but that's pretty useful for smaller water bodies, or if there's like creek arms in reservoirs. That could be also a really nice, maybe you do the back and forth over the main channel, and then in the creek arms, maybe you do the concentric circle. So it's whatever kind of is the most efficient way, again, to get that coverage. All right, so we'll just jump quickly to Google Earth, and kind of I want to show you just some tools on how you can create transects. I'll show you real quick GIS, Google Earth. I'm gonna actually show you on the Lorentz unit as well. So this is an example in Wisconsin. We're just gonna double click on this file here, and I just simply created a path, and you can just say you just want to and work your way around the shore. What's then nice about this, it gives you the distance, and then you can do your math. You don't want to be maybe 4 to 5 miles an hour, so you can get an understanding how long that might take you to get that coverage. So we'll cancel that. And if you create these files, you create these as KML, there is or KMZ, there's a lot of converters that you can convert these things to GPX to get them into your chart plotter or shape files. So all kinds of converters that you can use. So that's just a quick demonstration of Google Earth. Okay, feature tracing. Now we're going to jump to, hopefully this didn't lose my sync. I'm going to zoom out. Okay, good. It's still here. This, so Eryn's going to talk more about this reservoir. This is at Belleuse Reservoir in North Carolina that she and colleagues, two crews mapped. And this is actually the map she created. And you can export this out of Biobase. You can create your own custom charts. You can and then get them to read into the Lorentz. And what I did here is this is if you enable overlay Genesis Live is a live contouring feature. So and as you're going out there, let's say in a reservoir like this where the creek channel is kind of hidden or a big navigable waterway, you can have that Genesis Live map running, and it's going to kind of give a live contour map. What you can then do after you are done doing your transects, you can create a route that's tracing the Thalweg. And that's all I'm doing here is I just use my finger and I just touched a new route. I just go new route, and then you can just, like I was showing you, you can create that route. Enter that. You just create that route, and then Eryn will she has a autopilot rigged up on her boat, and so you could have the autopilot actually run this course and get more detail of that channel. So that's another little tip and trick. Okay. ArcGIS, creating transects in Arc and QGIS. Oops. It's interesting. There we go. All right. So if you're an Arc user, I would search the fishnet feature in the toolbox, and that will create the transect design, whether you want parallel or perpendicular. Or in QGIS, it's the create grid function, and that does the same thing. And then those are going to create your whatever transect design that you would like. And then I said there's a ton of file converters out there. You can Google .shp to .gpx, KML to .gpx. There's one at the Minnesota DNR GPS. It's old, but it's very functional. I still use it to convert files from KML to GPX, and it and vice versa around the other way, and it works really well. So, okay, and we'll wrap up this first half on showing you how to create transects on your Lorentz. So let's do this. Go to menu. We're gonna turn on the regular map. Okay. Routes. White Bear Lake. I'm just gonna show this. And we'll create another one. There's another lake nearby. Here's an example of what the Lorentz will create. There's no way for it to kind of clip it to the lake boundary. So you would have to, just turn around at shore and then start heading back the other way. So, but it's pretty slick. And so where that feature is, you have to enable, it's kind of buried. It is kind of buried. So the first thing you need to do is enable the feature. It's called search and rescue. You'd never find this if you weren't on this call. you go to advanced settings, features, and there it is on the bottom. I enabled search and rescue. Then, now I'll start it maybe right here. You go to new search pattern, and we want, I'll just say it's 100. We want 150 foot transects. And let's just start search. It's easy to edit after we get it started. Here we go. Good. So search pattern. Oh, and by the way, we'll be sending out a PDF of all this and a video as well, so you don't have to remember all this stuff. So, all right, so now I'm gonna get this kind of fine-tuned here. Set A to cursor. Okay. And we're gonna go here and set B to cursor, and then set C to cursor, and set D to cursor. Okay, cool. It's a little wide, but yeah, I don't like it. I'm gonna set B to cursor. And set B to cursor. All right. Yeah, I think that's, yeah, I think now we just go convert to route. Oh no, okay. So let's say I want to make it go perpendicular to the longest shore. That's typically the most common back and forth transect design, is perpendicular to the longest shore. I don't know why it's called creeping, but that's what it is, to go the opposite, the other way. And then we're gonna hit start search, and you can see it should flip it. Okay. So now I'm gonna convert this to a route, and it's doing its thing. Takes a little bit of time. Okay. And then I think we just hit cancel now. There we go. So there's the route. There it is. So that's pretty easy to do, and you don't have to do any fiddling around in GIS. So, all right. Like I said, we'll get the PDF out to you, so you have there. We put together a bunch of little short videos, tutorials. Those are all here, and actually some publications. Actually, one of mine before, when I was with DNR in the early 2000s, I was doing some dedicated research to these questions a long time ago. But it's still interesting stuff to look back after all this time. There is still some good lessons to learn there, and yeah. And okay, so now without further, I'm sorry, I was not sharing my screen when I was talking about the other Transect design studies and resources. So apologize for that, but like I said, we'll get out the PDF with this information. So then the links are, you can then just click on the links. All right. So without further ado, I'll introduce Eryn Malloy. She currently leads Duke Energy's Aquatic Plant Management Program as a scientist in water resources. She is responsible for coordinating and executing environmental sampling activities, including aquatic plant management, water quality, and T&E species. She holds a dual master's degree from North Carolina State University in fisheries, wildlife, and conservation biology. And actually now she holds a tri-master's degree, right? After attending Biobase University, she can add expert hydrographer to her list of accolades. So anyway, so outside of work, Eryn enjoys kayaking, hiking, and traveling. So Eryn, go ahead, take it away.
All right, perfect. Let me go ahead and share. All right. Thank you for the introduction, Ray. So first question first, just I'm assuming everybody on the call uses Biobase, but maybe you don't right now. With our teammates, when we were looking at how to tackle this project, I been a BioBase user since about 2017, starting my master's program kind of end of undergraduate. And using BioBase, my team is like, why BioBase? Why would we want to use this software? So a few reasons why are quick feedback. We were able to upload our data files after data collection during the day. If we were going out to dinner or something as a group, we could upload the files and then come back and look at them as a group, and the file would, 99% of the time be complete and ready to go so we could look at it. The main question we were asking was for data validation. We were comparing today's data using bathymetry versus old topography data before the lake was impounded. And then BioBase is great for ease of processing off-the-shelf commercial grade equipment. Our current fleet has Lorances already installed. And then this reservoir changes its lake elevation throughout the day. And we had the ability to offset for multiple lake elevations over multiple days. So each transect, we were able to dial in exactly what that target lake elevation was so that we were truly comparing apples to apples instead of apples to oranges. Another part of our pre-planning discussion was what design would we use? We needed to know how long this would take so we could correctly allocate staff. And then was there any equipment upgrades that we could make that would produce a better image or product for our internal customer? So a little bit more about Blues Lake. Construction was completed in 1973. It's located in the Roanoke River Basin, which is part of the Piedmont of the northern end of North Carolina and the southern end of Virginia. Blues is about a 4,000 surface area of 4,000 acres and has 88 miles of shoreline. Just kind of a sneak peek. This is some of the data that we collected on Blues, and knowing exactly where the channel was educated our survey design selection that we chose. So knowing that it was the deepest part was running north-south on our survey design, we decided to go opposite and run perpendicular to that feature that we really wanted to highlight, and went with 35 meter space transects totaling about 346 miles. We calculated how long this would take us to survey. We just did 346 miles divided by an average of 4.5 miles per hour travel speed and came up with 76.89 hours actively mapping on the water. And we created all this using ArcMap 10.9.1, which I'm holding dearly, holding on for dear life to ArcMap until it gets phased out completely. But that is the basis for our design. Obviously, you can kind of see in some of these coves back here that the lines are not connected, so we're missing that on the total mileage estimate in the beginning, but just using the fishnet feature in ArcMap, this is what we were able to come up with. The other question, what equipment upgrades could we make? We decided to use 2 Carolina skiffs, which is a fiberglass center console boat. We decided that having more boats would mean less time on the water, as well as should something happen, we would have a backup boat and would not be waiting to collect any more data. We also decided to upgrade our transducer to an Airmar TM260, which I'll show a little bit more about later. And this was recording data at 200 hertz with a 6-degree beam. We also decided to spring for the autopilot, just given the size of Blues and knowing that we were going to be taking some long runs, having the autopilot or anything really to help us make this as simple as possible and collect repeatable data was of importance for us. And with that, we also got an additional GPS antenna or puck for heading on the water. So in practice, what this looks like, so the black lines in the background, you can see are our transects that we imported out of ArcMap onto the unit. The green line shows where we've been, and the red line is the course of the autopilot. If you decide to go for autopilot, there's a few different ways that you can go about using it. We had never used autopilot before, and the learning curve was extremely easy. So we dropped a few pinpoints or a few waypoints, and we're able to enable the autopilot to navigate to the waypoint. And later on, we figured out some different tips and tricks as far as just holding the heading or anything like that, that just made it a little bit easier and less button pushing for the operators. So sampling in action, some features that we really enjoyed using in Biobase and our manager enjoyed too, was being able to use the report feature for percent complete to estimate our amount of the water body surveyed. So at the end of every week or before we'd start the week, we'd say, hey, we're about 78% complete or whatever that number was, and be able to give our manager and our customer some ballpark time of how much we had left to survey. Like I showed you in the previous slide, tracing the transects with a new color to show the areas surveyed was very helpful, as well as if crews were tagging in and tagging out, you could know exactly where people had been and did not have to repeat any lines. And then we also enjoyed that Biobase is very mobile friendly, and if we missed a spot, we could see exactly where we had missed it and go in and fill that gap if we didn't want to do it with the buffer. Just for example, where the pink circle is around the gap there, we were able to pull it up on our phone and navigate to that and find that missing piece of the puzzle. And it wouldn't be fieldwork without something going wrong. We had a few lessons learned. The biggest one was just to check the equipment. Nothing was inherently wrong with it. It was an operator error where we had crossed over a boom and kind of pushed the transducer into a cockeyed offset position. But through this, we were able to figure out, now we know if we see a bad output or what that would look like, which on the top right, that's the composition layer selected in Biobase. And you can see that it's that very light tan color that's saying that everything is soft. And seeing the rest of the lake, we knew that that was not accurate. And then also being able to see the sonar file on the bottom, you can actually see where it was slanted backwards. So those were some valuable skills that we were able to gain from our mistake. And we were able to correct this and get an updated merge and get rid of that data. So there was no way it would be used in future processing. And the biggest thing is balancing time and outputs, what our goals are for the project. We had talked about the waffle design or a crosshatch pattern. Some of our people in our group were really, thinking that that was the way to go. And a lot of people had never used Biobase before, but after going through it as a group, we were able to show, hey, this is good. Let's just keep going with this. And we're able to produce a good image for our customer. And I'll kind of show you on the other end. So if you're looking at upgrading your transducer, there's a really handy website, and I can put this in the chat also. Like I said, this was an Airmar transducer that we used, a TM260, but you're able to go in and kind of select different models of transducers that they offer, and also show that difference in the beam or the hertz. You can go in and see just how that beam changes over time, or how deep or not deep the beam will go. So just a neat feature there, worth exploring. And then going into Biobase, we can see all of our merges that we would go in as a team and look at. But we'll look at this one. So this is a section of blues. It's not the complete lake, but just kind of to show you how we were able to use this. So the red track shows all of our lines that we actually surveyed. One second. And then we were able to go in and also see with the composition feature, we had suspected that some sedimentation was occurring in the tributary that feeds into Blues Lake. And we're able to kind of confirm some of those assumptions, showing that there's a softer substrate there as compared to the center channel, the main area where water's flowing, that is showing a more hard substrate. And then are just able to go in and get some really detailed contours that would be pertinent for any future projects going on Blues. And then just looking at this feature or the report again, you can see the percent of the water body surveyed, and that's what our team was really interested in, as well as get some preliminary assumptions. And yeah, that's all I've got for you on Blues. I will also share my contact info in case anybody has any questions later. But we also have about 10 minutes now for questions. And yeah.
Eryn, I have been meaning to ask, and I don't know if you know off the top of your head, but like how many hours or days did you kind of put into this project, and you've got full detailed bathymetry basically complete for 4,000 acre reservoir? To me, that's pretty amazing, right? Because you started this in December, and I don't know if you did done any of those calculations. Oh, you're on mute.
Good catch. I should know how Teams works by now, but
Oh, you bumped it. That's okay.
yeah, for yeah, so we've asked if we traveled 354 miles on the lake divided by that time, and then the planning part was not terribly difficult. We've got some GIS whizzes in our group, and using the blog feature on Biobase, we're able to go in and really get those transects and plan it out that way. But I'd say under, including survey time, under a month for a 4,000 acre lake, which is, I mean, we had some weather challenges along the way. Had a few snow days in North Carolina, but no, it was pretty painless.
That's great. That's great. Yeah. Any other questions? Have at it. Like I said, it was a relatively small group here, so you can, yeah. Or any kind of ideas for, future webinars or expanding on issues? Yeah, Parker, go ahead.
Ray, quick question for you. So it looks like now for the data offset, you can apply a single offset to all your trips rather than having to do each one individually, right?
That's correct. Yes.
Okay. And do you have to, like, we have a couple different boats we use that have different offsets. Do you just update that offset prior to uploading your individual files?
You'd only have to do it once for your login. So every time you log in, that offset's going to be there. But if you've got multiple boats that have different offsets or different offsets of the transducer, then I'd almost, unless you're doing a lot of file uploads at once, then you'd have to go into their processing preference each time and update it. Otherwise, you can always go on an individual trip by trip basis and do it that way as well. And also something to think about, if you ever have to correct for water levels, you're going to need to do that on a trip by trip basis anyway. So the global processing preference probably is not going to be useful in that case. But if your water levels are always kind of very stable and you're not offsetting to the water level, then and that's the processing preference, the global processing preference is a pretty good feature to save yourself some time.
Well, thank you.
Yeah. Kevin.
I guess something that just popped into my mind about that same question, that this isn't my original question, but you know, for us in Florida, mapping 50 or so lakes a year and mainly just mapping for vegetation, we rarely incorporate offsets because we're mapping with so many different boats statewide, number one. And number two, right, correct me if I'm wrong, Ray, but if you're mapping for vegetation, you add an offset or you correct for an offset, and the vegetation is truly topped out 100% in 10 feet of water, and you add a 1 foot offset and reprocess it, it would change that that vegetation that was truly 100% to 90%, correct?
That is correct. It does not make the vegetation longer. It just
Proportionally,
adds
yeah.
water onto it.
Yeah.
So the plant height would stay the same, but the biovolume would go to 90%.
Okay. And then
yeah.
my original question is, you know, for depth mapping, which we do a handful of lakes a year, you know, obviously the depth of a lake does not stop at 1 foot at the shoreline, but that's the increment at what Biobase goes to. Can you go in and manually add, say, known depths of like half a foot and reprocess, and would that then change the depth increment to like a half foot?
Yes, it would. And thank you. Let's see. Let's give this a shot here. Great question. And I think I have an example of this here. This is a great example. This lake, as you can see, is just nasty shallow up here. And this person who surveyed this is the merge. They did not go all the way up in here, but it was all half foot deep. You right click, and then here you can add manual data. You can either add manual biovolume. This is another great example. If we clear everything off, come on, you can see again. If you can see, it's all topped out, really nasty stuff. So we can let's just look at the vegetation. We can go and we can right click, add manual data, add depth or biovolume. I actually did that here, and you can see the manual data. I added all the manual data there, and that goes into if we look at the report, it will say, does this include edited data? Yes, we included some manual data in there. It adds all the data here. The data will come out in the point data layer. It will get incorporated. The new manual data will get incorporated into grid, and it's a way you can kind of manually add data that you can't get your.
But had you added some manual depths, which I guess I've never done, would it change the depth increment? Like, would it go to like a half foot in those areas where you add?
Yep.
Okay.
Yes. Absolutely. Oh, great. All right. Any other questions? Great. Well, thank you all for attending. We'll get the video up on YouTube. We'll share that link. We're going to share the PDF with you. And yeah, let me know. Always, you can contact us anytime with questions. And yeah, you'll be hearing from us soon about EcoFish. Thank you.